Now we can finally start talking about the stability of fixed points of nonlinear higher dimensional maps. And just to set the scene, let's recap again that for the one-dimensional case, what played an important role was the derivative there and its magnitude in relationship to 1. And derivatives, as we've mentioned before, they're basically a linear approximation to that map because you construct the tangent line. The goal would be to figure out how we can construct linear approximations to higher dimensional maps. And just to get going, let's recap this linear approximation business for the 1D case. So pause the video and write down a relationship between the value of the function at the fixed point P and a point which is a little bit away, let's say, which is h away from our fixed point P. So pause the video and construct this linear approximation. So Mr. Taylor tells us that if we look at f of p plus h minus f of p, that will be equal to the derivative of our 1D function, the f dx, which we evaluate at our point P, around which we construct the approximation, times that distance h here, which separates 2 points, and then a bunch of error terms, a bunch of higher order terms, which will basically scale as second order with respect to h. Okay, this is our linear approximation of a 1D map. Let's now go to a higher dimensional map, but let's take one step in between, where we look not at maps, but at a function which is more dimensional. So it spits out a single number as an output, but it has multiple inputs. Let's say n inputs, x1 up to xn. So we can write this as f of vector x here. So pause the video and now write down the Taylor expansion type thing for this particular situation, where we have multiple inputs and a single output for our function. Okay, so in a very analogous fashion, now we can write down something like f of p, which becomes a vector. H is also a vector now. F is still a scalar, f of p. Now in this case, you will not have a single derivative. You will have all sorts of partial derivatives with respect to the different coordinates. So you will have a term like the partial derivative of f with respect to x1, which you evaluate at the point P, and which you multiply by the x components of our distance, of our difference vector h. And then you have similar terms for the other ones, ending with df dxn, evaluated at the point P times hn. And then, of course, there's a bunch of higher order terms, which we're not going to bother with, which is the order of h squared. Okay, so now we're almost there. What we need to turn this into a map such that we can repeatedly apply the map where the output goes back to the input is we basically need n of these functions. So we would have a vector function as an output, right? So this is taking n inputs and spitting out n outputs. And in essence, that's just a collection, a vector of different functions, like, for example, the ones we just had. But rather than just having a single one f, you have f1 up to fn. Okay, so pause the video and now construct the linear approximation for this case. What we in essence have is not just a single equation for f like we have here, but rather n different equations, one for fn all the way up to one for f1 all the way up to fn. And we can actually rearrange this into a more compact matrix formulation as follows. So if we now construct our approximation, now f becomes a vector as well. So we have f of p plus h minus f vector of p vector in this case. So let's first look at f1, for example. So we can write this in a matrix form as this. We have df1 dx1 all the way up to df1 dxn. And if we have here h1 and then hn, if you just multiply this row with this column over here, you basically have the equation that we had up there, but replacing f by f1. But now we don't have just a single one of those f's. No, we actually have multiples of those. And for each of those, we can have a different row in this matrix. So finally, at the final row, we will have dfn dx1. Then we have dfn dxn. And obviously, all of these derivatives, they're evaluated at our point P around which we develop our function. And again, as usual, we have some higher order stuff that we don't care about. Excuse me. So now we have this matrix of derivatives, which is very important and which has a special name. This is the Jacobian matrix of this map here. And you can write this down, for example, we will write this down as df evaluated at the point P. So very important concept, the Jacobian. So now we have constructed some sort of linear approximation to our nonlinear map. And let's now make the jump towards the stability of fixed points over here. So let's start from a situation where P is not an arbitrary point, but actually a fixed point. And let's also try and figure out what happens to the distance h that we are away from the fixed point, and what happens to the distance after you apply the map, because this will be important for stability, obviously. So pause the video and try and figure out what this map does to distances away from the fixed point. Okay, so since we have a fixed point, P, if we apply the map f to that fixed point, we end up again at P. But now let's look at a point in the neighborhood of P, distance h away, with h being a vector. If we now apply our map f, well, the formula we've just written down will tell us that this will map, of course, to f of P plus h. But this is actually equal to f of P plus then our Jacobian matrix, the fp times this distance vector h. Since we have a fixed point, of course, f of P is equal to P. Now, if you look at these equations, what this basically tells you is that if we start from an initial condition which is h away from P, then that difference h, the difference between this point and that point, after applying that map, that difference from P, because this is P, the difference will be given by this thing here, by h multiplied by our Jacobian matrix. Or to make it a little bit more explicit, if we start from a distance h away from the fixed points, after we apply that map, that distance h will have scaled to the fp times h, which is, of course, a linear map in h. So as long as our distances h are very small, the behavior of our nonlinear map in the region around P can be approximated by an equivalent linear map operating upon h here. And that, of course, will give us inspiration for how to tackle stability, because we know how linear maps behave in terms of stability. What we should do for linear maps is we should look at the eigenvalues of that map and then look at their magnitude. So if all the eigenvalues are smaller than 1 in magnitude, we have a stable sink. If they're all bigger than 1, we have an unstable source, fixed point. And if we have a mixture of stable and unstable, we end up with saddle points. So it's actually very plausible, the argument I made here, but I'm not going to formally prove it. So that would be a little bit more elaborate. But I think it's very intuitive that the way you handle this here will work. So you'd have your nonlinear map. you construct a linear approximation to it, and then you look at the eigenvalues and the eigenvectors related to that linear approximation related to the Jacobian matrix.